Welcome, folks. Today we are discussing a paper comparing bio-inspired techniques for tracking maximum power in photovoltaic PV systems under variable environmental conditions.
Interesting. What are the main bio-inspired algorithms compared in this study?
The study compares four algorithms: artificial bee colony, ABC, particle swarm optimization, PSO, genetic algorithm, GA, and a newer algorithm, jellyfish optimization, JFO. They're all used to track the global maximum power point, GMPP, of a PV system.
And what were the environmental conditions considered?
They tested under three conditions: standard test conditions, STC, step change irradiance, simulating sudden changes in sunlight, and partial shading conditions, PSC, where parts of the PV panel are shaded.
So, how did they evaluate the performance of these algorithms? What metrics did they use?
They used several key metrics: maximum power tracked, total execution time, number of iterations to reach GMPP, tracking efficiency, and root mean square error, RMSE. They also used regression analysis using Minitab software to model the PV system's power voltage, PV, curve under each condition. The R-squared value was near 1, indicating a good fit.
I see. And what were the main findings? Which algorithm performed best? The JFO algorithm consistently outperformed ABC, PSO, and GA across all three environmental conditions. It achieved higher tracking efficiency, 98.9%, faster execution times, 0.0386 to 0.1219 seconds, and a lower RMSE value, 0.59, compared to the other algorithms. That's a significant improvement. But how does the JFO algorithm work in a nutshell? What makes it so efficient?
JFO is inspired by the foraging behavior of jellyfish. It uses a time control mechanism, considers maximum food availability, representing maximum power, and incorporates both active and passive movements of the jellyfish to explore and exploit the search space efficiently. The algorithm balances exploration and exploitation well, leading to faster convergence to the optimal solution.
I'm curious. The paper mentions using regression analysis to model the PV system. Why was that necessary? Couldn't they just directly compare the algorithm's performance on the simulated PV system?
That's a good point. The regression analysis was crucial for creating an objective function. The PV curves are complex and nonlinear, especially under PSC. By fitting a regression model to the PV data, they created a mathematical representation of the system's behavior, which the optimization algorithms could then use to find the GMPP. This approach allows for a more rigorous and quantitative comparison of the algorithms.
Okay, that makes sense. Did the study consider any limitations or future work?
Yes, the study acknowledges some limitations. They didn't consider factors like air mass, wind, module heating, soiling, panel orientation, and humidity, which can all affect PV system performance. Future work could incorporate these factors for a more realistic simulation. Also, testing with a wider range of PV module types and sizes would strengthen the conclusions.
So, in conclusion, this paper presents a strong case for the JFO algorithm as a promising technique for MPPT in PV systems. Its superior performance across various conditions suggests it could be a valuable tool for improving the efficiency and reliability of solar energy systems.
Precisely. The JFO algorithm shows great potential for real-world applications, offering a significant improvement over existing methods. Thank you for joining us today, folks. We hope you found this discussion insightful. Goodbye.